Each asset is worth an amount that is an exponential random variable, right? So you have alpha of them, and X is defined as the maximum of the amounts of each asset, right? And the first part is to find the CDF of X, right? I mean, that shouldn't be too difficult. So let's see how we can do that. So this is part 1 of tutorial sheet 4. So you have X equal to the maximum of x1 to x alpha, and we want to find the CDF of X, right? Yeah. All right, and you write this as, you write this as the probability that the max of x1 to x alpha is less than or equal to alpha. Right, and this, because the maximum is less than or equal to alpha, means that each of the random variables has to be less than or equal to alpha, right? Okay. Now, because of independence, you can write this as the probability that x1 is less than or equal to x, all the way up to the probability that x alpha is less than or equal to x. Okay? The audio is unclear. I'm trying to make it clear, sir. I don't know what the problem with the audio is. We had the same problem last time. I will okay, good morning. So this is the CDF of the exponential random variable with parameter lambda. So this is, I'm sure all of you know, this is E of 1 minus this, right? And this is the CDF of an exponential random variable. And this is also the CDF of an exponential random variable. Okay, so if you multiply all this, you get this. Hello guys, you still have problems hearing me? I don't know why. I'm using a microphone, but it's still, I don't know why. Okay, hopefully. All right, so are you guys okay with this? Any questions on this, guys? Yeah. So this is question 1 of sheet 4. Question 2 is to find the density function, or the PDF of X. So basically you need to differentiate the CDF with respect to X, and if you do that, you will get alpha this is what you will get. Yeah, and this, you can write this as alpha lambda because these two are constants. So this is part 2. This is part 2 of sheet number 4. Right. Now, the next part is to find the nth moment of x. Right. Now, to find, when I say the nth moment of x, I mean the following. So this is part 3. The nth moment means the expected value of x to the power n, right? So in this case, this will be the integral, because you're dealing with the continuous random variable. It's the integral from 0 to infinity of this multiplied by the density function, which is this one here. So it's alpha lambda all right. So you need to basically work out this integration, right? Obviously, integration is something that you learn by experience. So there's no rule for doing integration, right? So there are many ways you can do this integration, but I would do it like this. All right. First of all, let's take the constant alpha lambda outside. So this is alpha lambda times the integral from 0 to infinity of all right, in the next stage, the next thing you need to do is to make a substitution. So in this case, I'm going to make the following substitution. So set y equal, okay, so x is minus 1 over lambda times log of y. So dx by dy is going to be minus 1 over lambda times 1 over y. So let's put this in a box. All right. Let's put this in a box. Now I'm gonna sub this into this integrand, right? So if you do that, you get alpha lambda. Alright, first of all, the limits. When x equal to 0, if you put x equal to 0 into here, you get y equal to 1. And if you put x equal to infinity into this, you get y equal to 0. Right? Then this becomes and dx will become minus dy divided by lambda y. Okay. Okay, a few things cancel out. The lambda here and the lambda here will cancel out. The y and this y will cancel out. Okay, and you have a minus here which I'm going to take outside. So it's going to be minus alpha. Are you guys following me or not? If you're not following, let me know. Okay, minus alpha, the integral from 1 to 0 of I'm going to write this as Yeah, are you with me so far? Okay, now in the next step, I'm going to use this minus sign here to switch the limits. Remember, you can use them, if you multiply some integral by minus, you can switch the limits around using the minus sign. And also, I'm going to take this outside, so it's going to be alpha yeah. Alright guys? Okay. Alright, this is where the next trick. And you may recall that I think I might have mentioned this before. I think I did. Sorry. That you can write, if you have something like x to the power beta and you're differentiating with respect to beta, right? Then this is, I think I mentioned this before, is x to the power beta times log of x, right? Is that right? Yeah? Now, if you do this n times, you get, in other words, if you differentiate n times with respect to beta, okay, the formula that you will get is this, right? Okay. Now what I'm going to do is, if you put beta equal to 0 on both sides of this equality, you will get on the left hand side you will get this, and on the right hand side you will get log of x to the power n. So let me put this in a box. So this is, let me put this in a box, right? Okay, and in the next step I'm going to use this box, right? I'm going to use this this fact here to replace log of y power n by this. You follow what I'm saying? So I'm going to use this, right, to replace log of y to the power n by the left hand side. So this is alpha, sorry guys, my writing is not good. Okay. Okay guys, you follow what I've done. So I've used this fact here to replace log of y power n by this guy here with y in place of x, right? Okay, now I'm going to take this, what this means at beta equal to 0. So I'm going to take it outside of the integral. So I'm going to put the sign beta equal to 0 outside of the integral, right? And in the next step, let's take this outside. In the next step, I'm going to take the derivative outside of the integral. Okay, so you see what I've done. All right, and in the final step, I'm going to use another fact. I think you should go to the course website. There's a video on something known as the beta function, which is defined like this. This function is known as the beta function, and there's a video about this on the course website. I don't know if you have seen it already or not, but you should go to the, you know where the course website is, right? You should go to the course website. You will see a video about this function and the properties of this function. Okay, so please have a look if you haven't done it already. Right, so using this definition or using this function, you can write the integral as the beta function at beta plus 1 comma alpha, right, taken at beta equal to 0. So this is the answer to question part 4. Was it part 4 or part 3? Part 3, sorry. Part 3 of tutorial sheet 4, right? Okay guys, any questions on this, please let me know. Those of you on Zoom, you have any questions on part 3? Hello guys, talk to me. Any questions on part 3 of sheet 4? All right. Another way you can write this is to, there's a property. There's a property of one of the properties of the beta function I mentioned in the video on the course website is the following. Right, you should go, once again, you should look at the course website, you will see this. Right, so using this property, you can also write this result as follows. Yeah, you can write it as follows too. Yeah, so that's another representation for the answer for part 3 of question. Yeah, you guys okay? Any question on for those of you on Zoom? Any questions, guys? Let me know. All right, so that's part 3 of the tutorial sheet. Now part 4 is to find the mean, of x. Remember, the mean is simply the expectation of x, right? So to find the mean of x, all you have to do is simply, so this is, here we are. So this is part 4 of sheet 4. So to find the mean of x, all you have to do is put n equal to 1 into this formula, right? So if you put n equal to 1, it becomes alpha over lambda d by d beta of okay. So this is the mean. I'm sure you can. I'm lazy. I mean, I'm sure you know how to differentiate this, right? I will let you finish it, okay? Part 5 of sheet 4, you are asked to find the variance of x. Remember, the variance is the expectation of x power 2 minus the expectation of x, like this. Right, now to find the expectation of x power 2, you put n equal to 2 into this formula, right? You follow me? Yeah? So if you put n equal to 2, you get alpha divided by lambda squared Alright, this is what you will get if you put n equal to 2. Yeah, and then you take away the mean, or the square of the mean, which we already worked out. Okay, guys? So that completes part 4 and part 5 of sheet 4. So again, please do the differentiation. I'm sure you can do it better than I do. Okay, so please do that, alright? Any questions so far? You okay? Okay, you alright, man? Veronica, you okay? Yeah. Alright, part 6 and part 7 you won't be able to do because I haven't covered the material. I haven't covered the material for 6 and 7. 6 is asking you for the value at risk, and 7 is asking you for the expected shortfall. You won't be able to do them until for another 2 weeks or something, right? So ignore those. So can you do the last part, please? I don't want to do all the parts. So I'll give you a few minutes and see if you can do the last part of sheet 4. So take a few minutes and see if you can do it. All right, guys, just take a few minutes because I don't want to do all the questions. So, all right, to do this last part, just assume x1 right. All right, assume that you have a random sample little x1 to little xn on the variable capital X. Remember, capital X represents the most expensive asset, or in other words, the value of the most expensive asset is X, right? And we are supposing that we have n data values on X. So the question is to find the MLE for alpha and beta. Yeah, I mean, there are other ways you can do it. There's no one way. Yeah, you can do that. Okay. I mean, that's just one thing. I mean, you do it another way. You can do it another way. Think about it. It's not something to do.
No, I think it's without.
Yeah, sure. Okay. All right, guys, have you done it or not? You done the last part? All right, let's see how we can do it. So the first thing you need to do is to write down the likelihood function. Yeah. So this is part 8. So you have two parameters, alpha and lambda. All right, so it's gonna be and the likelihood function is the density. Remember, it's the product of the density function. In this case, is the density function of x, right, which we derived in part 2. So we derived the density, the PDF in part 2, which is okay, guys, you with me or what? So this is the density that we derived in part 2 of sheet 4, right? So the likelihood is just the product of this from 1 to n. Now if you simplify this, right? Okay. All right. The next step is to take the log of the likelihood. Yeah, and the next step is because you have two parameters, we need to do the partial derivatives with respect to alpha and with respect to lambda. Okay, so let's first of all take the partial derivative with respect to lambda. You get this, and you have to set this to 0. Call this equation 1. With respect to lambda, yeah, correct me if I'm wrong. So these are the two. Please mute. What's happening? It's already muted. What? Hello? Can you write in English, please? All right. So, all right. Now, to solving these two equations is not easy analytically, but you can simplify them a bit. So, for example, from equation 1, you see that alpha is minus n over and let me call this equation 3, right? So equation 3 expresses alpha as in terms of lambda. So now what I'm going to do is I'm going to substitute equation 3 into equation 2. Excuse me. So if you substitute 3 into 2, you will get the following. You get you get this, right? Now let's call this equation 4. Now if you look at equation 4, you see that there is only one unknown parameter in equation 4, which is lambda, right? So basically you can solve this equation 4 using pretty much any software. I mean, there are many, including in R. I'm sure most of you know R. There are many software in R for solving equations that have only one unknown, like equation 4, right? So you can, I'm sure there are other programs also, but so solve 4 to obtain the MLE lambda hat of lambda. And it's easy to do that. There are many software for doing it. Now once you got lambda hat of lambda, substitute lambda hat into the right hand side, right hand side of equation 3 to obtain alpha hat. See, if you look at equation 3, the right hand side involves only lambda. So if you replace the lambda in equation 3 by lambda hat, that will give you the MLE for alpha hat. Okay guys? Excuse me. Any questions? You okay or no? Any questions on Zoom, guys? Can you hear me on Zoom? So can you show the hint for quiz 3 again? Oh yeah, okay. Yeah, I know some of you came late, so let me show that one more time. So, I mean, this is a hint for quiz number 3, but you don't need to follow this hint. You do not need to follow this hint. I mean, there are other ways you can do quiz 3. I mean, as you know, in mathematics, I mean, a problem can be done in many different ways. But one way to do this is to use this hint, right? That is, if you have something like 1 minus z power b and z approaches 0, then you can replace 1 minus z power b by 1 minus b times z. Okay guys, that's the only hint I can give you. Otherwise it shouldn't be difficult. I mean, you shouldn't be difficult to do quiz 3. Yeah. Yeah. Any other questions, guys, on the Zoom? All right. So we will. So next week we will talk about case 5 and case 6. Because remember, on Wednesday this week we talked about case 1 to 4, right? So next Wednesday we will talk about case 5 and case 6 of portfolio theory. All right, and the week after next week we will talk about risk measures. So that's where we talk about value at risk and expected shortfall. Yeah. Okay. All right, guys. Have a good weekend. And if you have questions, as usual, feel free to contact me 24/7 by email or Skype or Zoom or phone. I gave you all my contact details, so you shouldn't have problems. Okay. All right. Hi, how are you?
Yeah, good. You mean the hint for quiz 3 is this one and z tends to 0? Or?
Yeah, that's right, yeah.
So we have
this, if z approaches 0, then you can replace this by this.
So, yeah, and we just assume that gx tends to
No.
wg.
Yeah,
WG
this
tends to
doesn't go to 0.
I know. I mean the f and the g, the function f and g.
Yeah.
The f and the
Yeah,
same.
they're the same. Yeah, you need to assume that. Yeah.
So we can assume this to 0 and replace this to this. Yeah.
WG, no, it doesn't need to be 0. WG doesn't need to be 0.
Yeah.
WG can be anything.
Oh yeah.
Can be anything.
Yeah.
Yeah. So, but if you have a situation where you have something like 1 minus z, where z approaches 0,
Yeah.
then you can use this result.
Okay.
Yeah. Think of,
Thank you.
yeah. Just think about it. If you need help, just contact me.
Okay.
By email or Skype or Zoom
Okay.
or phone. Yeah. Hi.
Hey, the intuition for the quiz, I think you had explained in a few lectures, was that you like assume F is gumball and
Yeah,
show
yeah.
J is gumball, assume.
Yeah.
Right.
That's right. Yeah. There are actually, you should go to the course website. There are many examples like that with solutions. There are. I mean, those of you who are, if you are struggling, then please look at the course website.
Started, I was just checking.
Yeah.
Sometimes, like, for example, max domain of attraction.
Yeah.
You haven't said the word in the lecture videos. Like the first time you mentioned
Yeah,
maximum domain of attraction
Yeah.
was in the
Tutorial. Yeah.
tutorial, yeah.
Yeah. It just, I mean, there are many questions, Mathis, on the course website.
Yeah, I haven't even tried. I don't know if it's difficult or anything. I'll try.
It shouldn't be difficult. If you have problems, just contact me.
Yeah.
Okay. All right. I mean, there are many examples similar to quiz 3 on the course website. Like if you look at the past exam papers, every past exam paper has a similar question. So just look at it. And if you still have problems, contact me.
Has the course changed since the release of the latest
No.
papers?
No, it's the same. I mean, all the past, whatever, I don't know, like 6 or 7 years, they are similar. They are all similar. And
All based on the same syllabus.
yeah, yeah, yeah.
It's like a formula in the notes where